Okay, welcome to page 104. We are looking at the summary box about halfway down the page there, and this is the continuation of example 1b on page 102. Let's read the first part of the summary together here. So it's telling us that A is an n by n matrix that has eigenvalues lambda 1 through lambda n. Some of those might be repeated, and linearly independent eigenvectors v1 through vn that correspond to those eigenvalues. And they emphasize in this problem that the vectors are actually linearly independent. If all of that is true, then it turns out that A is diagonalizable with D equal to Q inverse AQ. In other words, we can diagonalize the matrix A using that formula. Okay, now before we go further and write down what D and Q are, I want to point out that this is exactly the same equation that we found back in example 1b. In that example, n was equal to 2. We had a 2 by 2 matrix, and we had 2 eigenvalues and 2 linearly independent eigenvectors. Same situation as here. So this summary that we're in the process of describing is just a generalization of what we noticed in example 1b. Now, what was special about those two matrices D and Q? Well, if you look back at the matrix D that we found, it was diagonal, and along the main diagonal it had the eigenvalues of the operator. Okay, and that's going to be true in general. D is going to be a diagonal matrix with the eigenvalues down the main diagonal. What was special about Q? Well, Q had as its columns the eigenvectors. Okay, so it looked like that. And the one comment that I'll maybe make here is we want to be consistent with the order in order for this to work in general. So for example, we chose to put the eigenvalue lambda 1 here, therefore it's important that this v1 be the eigenvector that went with that first eigenvalue. Similarly, lambda 2, we need the eigenvector v2 to be the eigenvector that corresponds to that lambda 2, and so on down the line. We just need to be consistent with those two orders, and if we are, then this diagonalization formula is going to work out for us. Okay, just a couple of notes then before we move on here. First, reminds us that A is diagonalizable if and only if A has n linearly independent eigenvectors. And remember what the n is. That's the size of our matrix. So whatever the size of your matrix is, you have to have that number of eigenvectors basically in order for this to work. Okay, and the second comment gives us a little bit more information about this matrix Q. We already mentioned above that Q has eigenvectors as its columns. This is giving us a little bit more information by pointing out that Q is actually a change of coordinate matrix. And in particular, it's the change of coordinates matrix taking beta prime coordinates, where beta prime is the basis consisting of our eigenvectors, to beta coordinates, where beta is the standard basis. Just another way to think of this matrix that we talked about. That concludes this summary, and we're going to see in the next section that this diagonalization formula is very handy when it comes to making matrix calculations.